So now let's talk about an example of regression and in the literature and how we might use it. So the example I'm going to use is from Cortina et al., Cortina, Goldstein, Payne, Davison, and Gilliland from 2000. And the article is the incremental validity of interview scores over and above cognitive ability and conscientiousness scores. And this is from an issue of Personnel Psychology. So this is a seminal and important article that eventually gets to the idea that structured interviews add validity and add predictive validity over and above cognitive ability and conscientiousness scores. So we'll get to that in a later video. Their initial prediction, though, in this is that cognitive ability predicts performance. This is a well-understood, well-known relationship throughout IO psychology and in the workplace, but it's a good starting place for our discussion and our example today. So I have this example from Cortina 2000, and I want to go ahead and use it. So I'm trying to predict job performance from cognitive ability, right? So if we're using our X to Y relationship, I'm predicting job performance as an outcome from cognitive ability. So if you remember back to the first week when we talked about multivariate, we talked about model building, right? So the video on model building set up some rules about what we're going to do. So first thing we have to do, first step of model building and testing the model is to define the model, right? And so in this case, the first question we ask is what are the constructs? The constructs in this case are cognitive ability and job performance. And then the second question is how are we measuring that, right? And so there's lots of ways to measure cognitive ability, SAT scores, IQ scores, other tests of cognitive ability. And then how are we measuring job performance? And this, of course, is a huge question that we ask all the time. How are we actually measuring job performance? Performance rating from managers, 360-degree evaluations, performance on particular tasks, organizational performance, lots of different ways to measure job performance, right? So we have to answer those questions. And I'm going to hand wave it for the moment because this actually was a meta-analysis, so there's lots of different measures, but be aware that's an important thing. And then what type of analysis am I going to do? So now I've defined the model. Now my question is what type of analysis is appropriate? Now this is going to be a dependence analysis, right? Remember there's two kinds of multivariate analysis. There's independence, which is stuff like factorial factor models, and then there's dependence, where I'm trying to predict one variable from another. So obviously I'm trying to predict job performance from cognitive ability. That's a dependence model. How many variables are there? Well, in this case, there's one dependent variable and one independent variable. So there's a single relationship between the two. And they're both metric. So if I go down that flow chart, so if you remember back to Hare's flow chart and how to follow, if you follow along that flow chart, first question is it independence or dependence? It's dependence. And the next question is how many variables are there? In this case, two variables with one relationship. And then what's the measurement scale? Metric or non-metric? In this case, metric, right? We actually have measure of these things, continuous measures of these things. And this would bring us to using regression to find our results. So don't worry about the next step would be to develop an analysis plan. They collected the data, and in fact, this was a meta-analysis, which is a whole separate subject, but they collected the data and then worked out the assumptions. So the next step is evaluate your assumptions. We'll assume in this case, for the sake of argument, they evaluated their assumptions. Then the next step is now we're going to assess what we did. So we've analyzed our assumptions. Now we're going to assess our data. The first thing that we do is we assess global fit, right? The overall fit in this global statistics. Typically for regression, our overall fit is either R squared or F, right? So now we're talking about overall or global fit. And this is how well our model works overall. It's not about any particular prediction out of the model. It's does our model fit the data? We have a model, we collected the data. Does it overall predict the data? Not a particular relationship, but overall. That's why we call it a global fit. So we typically use R squared. R squared is referred to as the coefficient of determination. And that's very typical. The programs we use, SPSS and R, will also give you F. You'll see a lot of times in some older articles, people used F a lot as a global fit for regression. Typically though, in today's articles, and we'll talk about why later, we see R squared in the more modern studies. So these are our indices of global fit, right? And R squared in particular, since that's the one we use most often, we have to understand that is the overall variance that is described by the model. So if you remember back to when we talked about correlation was R squared, was literally Pearson's R times Pearson R squared. That told us the amount of variance in Y explained by X, by the variance in X. And that's what R squared is doing here. For our whole regression model, how predictive, how well does the variance in our predictor variables tell our overall, explain our outcome variables, right? And so that's our R squared. And then the next thing that you would do is you would estimate local fit, right? And local fit, these are the specific predictions that go along with each parameter, with each variable. So in an example where we have, well, if you have y being equal to bx plus a, right? Overall, how well this model fits the data comes from R squared. That's the global fit. But then when we estimate what is b, what is a, what is the estimate of any particular y hat, these are local fit questions, right? And same thing with the evaluation of beta. If we're doing a standardized regression equation, when we estimate that, that is a local fit. We do that after we determine if the overall model is good with the global fit. Then we determine the local fit. How are our individual predictions? So in this case, Cortina et al. 2000, let me show you what findings they had. So the correlation in this case between job performance and cognitive ability was 0.432. So if we're going to turn that then into a standardized regression equation, what we get is job performance is equal to 0.432 times cognitive ability, right? No y-intercept because it's a standardized regression equation. And this is beta, right? This is our standardized regression weight, beta, 0.432. Now, technically, it would be z-scores of job performance and z-scores of cognitive ability, but we don't typically notate it that way. So beta is equal to 0.432. R squared, in this case, is 0.187. So overall, this equation accounts for 18% of the variance in job performance. The ability of cognitive ability to predict job performance, it predicts about 18% of differences in job performance. So any particular difference in job performance, according to this study, we can predict 18% of that using cognitive ability. And then for every single, now when we interpret the standardized regression equation, we interpret it because these are z-scores, the interpretation changes a little bit. So instead of being a single point increase is worth this much point increase in the outcome variable, we talk about it in terms of standard deviation units. So one standard deviation change in cognitive ability is equal to 0.4 standard deviation changes in job performance, right? So if we have someone who's applying for a job who has cognitive ability that's at little less than a half a standard deviation, or excuse me, that's a full standard deviation above the average, then that person will have their job performance will be about a half a standard deviation above everyone else. For people who have 2 times the cognitive ability, right, they're 2 standard deviations away from the mean, they're going to have maybe a whole standard deviation difference in their job performance. So this is a pretty powerful predictor. In fact, it's the single most important and powerful predictor other than previous performance. Without knowing previous performance, the cognitive ability is the most important predictor of job performance. So, one thing to note here, that our R squared, it may seem kind of small, right? 0.187 on a big scale. It could go up to 1, right? From 0 to 1, 0.187 seems kind of small, 18%. But this is actually, like I said, 0.432. That's fairly strong. This is a relatively good predictor. So overall, even though this seems small, it's really about the relative value of it. This is more than we would get by not having anything else. And in fact, even when we do regression equations in medicine and in other areas, we find even smaller percentages. So we can't get too wrapped around the axle about this doesn't seem like too much. Anyway, so that's Cortina et al. Predicting job performance from cognitive ability. And this is how you would interpret, this standardized regression equation. A single standard deviation increase in cognitive ability is equal to 0.432 standard deviation difference in job performance. So, and again, this is bivariate regression. We have two variables, one relationship between the two, bivariate regression. This beta weight is the same as R, the correlation between job performance and cognitive ability. And that's how we go about interpreting our standardized regression equation.